Okay, so last time what we finished was this problem of max sum subarray, where you are given an array storing n integers and you want to find contiguous interval I to j such that ai plus 1 dot dot aj is maximized. So brute force was n cube, but we have given a clever algorithm which is only linear time, order n. Any questions? So this was possible because of two ideas. One was that we reduced an index. Instead of I and j, we just worked with j. And second was that you were lucky enough to have a very small update. The update of Sj was constant time. So you can do this in a single, essentially double scan of the array in just 2 scans. Is that fine? Okay, so now we'll look at a more challenging example, which is a 2-dimensional problem of local minima. And yeah, as an exercise here you can, which I actually already have stated, this change this pseudocode or modify, adapt this pseudocode to compute also the i's which you get. So you already know the Sj values, but what is the prefix which actually works? So this I to j calculation, also do this as an exercise. So adapt this pseudocode to also calculate the I array. Of the correct i's. Okay, so which would mean that you have calculated the prefixes and the sums that are maximized, the optimal ones. So the next problem is problem of 2D arrays, which is local minima in a grid. So you are given an n cross n grid, which is a 2-dimensional array, as you have seen in ESC 101 in C programming. And what you have to do is write a program whose input is so let me just say GNN. So it's a 2-dimensional array of integers. You can assume integers to be distinct, n square integers, and the columns, rows are indexed by 0, 1, dot dot n minus 1. And what you have to output is a local minima. So if you had to output minima, then how many steps will be required? Then you have to see every element in the grid in the 2D array. So that will be n square, right? There is no way that you can beat n square, because whichever cell you will miss, an adversary can put the minima in that cell. So this is a lower bound proof of n square. So we will not try that, because that you already know. What we will try is what you don't know, that is the local minima problem, which is you just want to output a cell whose value is minimum amongst the neighbors. So find a local minima. that is an entry Gij that is smaller than its 4 neighbors. So you have this I comma j cell, and its neighbors are the following. Okay, so this is I, this is j. So this will be I minus 1th row. Yes.
Are we not considering the corner elements?
Corner elements, yeah, whatever is available. So this is the general thing. But if the green cell is at the corner, for example, top left corner, then it has how many neighbors available? Just 50%, right? So then it has only the j plus 1 orange and the I plus 1 orange. So neighbors can be 2 to 4. Can they be 3? Yeah, so if you are at the edge, just below the top left and above the bottom left, then you won't have the G minus 1 orange. So neighbors can be 2, 3, 4. Whatever it is, the invariant or the property that we want in the output is the green cell value should be less than whatever is available. What is the question?
This is the elements that are in the corner. So this is our cell.
Yeah.
We are taking the card.
You mean the other 4? The other 4 we are ignoring. We are not looking at 8. The neighbors defined by a common edge, not by a common vertex. So yeah, this will be called the local minima if the matrix or the grid looks like this. So you have 3 here, and other values are bigger. Okay, so in this case, we can say that the green cell is a valid output. So unlike global minima, local minima output can be many. This is not unique, right? Because it is dependent on the orientation. But so you have to output just one, find one and output it. So yeah, so the question is, why does a local minima exist? That's the first basic question. No, that's not the answer. Somebody else, why does a local minima exist? So local minima exists because global minima exists. So wherever is the global minima, if you look at that cell, that obviously will look like this. So a local minima exists in G because we can always take so the global minima cell is also local minima. Because none of its neighbors can be smaller. So hence, there is no problem with existence, and generally they will exist many. You just have to output one. So the first idea is always the trivial idea, right, which is you scan the whole grid. So single scan of G yields a local minima. And what is the time? Yeah, time cannot be less than n square. So the pseudocode for this is just a single scan, and so it's single for loop or double for loop for I comma j, And the double for loop inside, what you are doing is just looking at the 4 neighbors and checking this picture, whether this picture holds. Right? This is a constant time operation. Assuming that the integers, etc., are small, we don't worry about that in this problem. So this is constant time operation. So you have constant times n times n. That is the time complexity, brute force. So the burning question here is, can you do this in order n time? Can you reduce the time complexity? Because for global minima, you cannot. For local minima, can you reduce the time complexity? In particular, can you make it order n? Can you? Is it possible? So order n basically means that you will simply not look at the whole grid. So there will be spots in the grid which will not be seen by you. So the adversary can do whatever adversary wants. Still your answer will not change. Right? So if this is possible, it will be a surprising thing. And we will obviously make it possible. But that will be a complicated algorithm. So you have to stay awake. Okay, so we will do it in multiple steps. As I said, it will be an algorithm which will have many ideas. So the first idea is, since it's a local problem, you do local exploration. Or iteration. So local exploration means that you can start from the 0,0th corner and go to the smaller neighbor, if it exists. If it doesn't exist, you can already output the answer. But if there is a smaller neighbor available, then you actually jump to that and then repeat. Okay, so that's a local exploration algorithm. So go to a smaller neighbor. And repeat. And obviously, if this doesn't exist, so if you can't, then you have found the answer. Right? So if there is no smaller neighbor available, I mean all the other 4 are bigger, then obviously you have this picture, so you can just output wherever you are. That is the local minima. That is one local minima. Otherwise, you just keep exploring. So the pseudocode for this is simple to implement, this local explore. So what you do is you start with initialized variable g00, and while c is not local minima, you can update C to be least neighbor. Right, so this is a single while loop. So it will break only when you reach a local minima. So at that point, you can just return that value. So it's a simple enough algorithm. What is the time complexity of this? Is this already a linear time algorithm? Can you show this? Sorry?
So we can like the worst, we can go for the worst condition, which can be like the smallest, the local minima is in the corner most point, like bottom right corner. So we are going from the top left to the bottom right. So what n root 2?
N root 2.
No, sorry, 2n.
Yes, so that is a suggestion. Others should try to show that this doesn't work. Okay, try to find a counterexample to this. So this is not n, this remains n square time. This is not a fast algorithm. So one property that can be shown here is that no cell is visited twice. So this is the first thing you can prove, that it doesn't get into a loop, which means that the while loop will break. Right, so why is this? It's not an infinite while loop. So this is because we have assumed the grid to have distinct integers, and every time we take a step, we reduce the value. Right, so value C decreases in every step. So the value of C is monotonically decreasing, which means in particular that the same cell cannot be repeated in this while loop. So that is the proof of this, which implies that while loop halts. But in how many steps will it halt? This is not clear. Because again, when the adversary sees this algorithm, adversary can design an input where you will be forced to look at every cell. You can design a sequence of neighbors so that no cell is left unexplored. So as an exercise, you can show this. There exists an input on which time is n square. So there is an input grid G which takes time order n square, and since our complexity is always worst case analysis, we'll consider this order n square. So on some or generally on most inputs, this algorithm will be faster than the full scan, but worst case it can be quadratic. So this is then no better than brute force. Right, so we have not made progress in terms of time complexity. So what is the use of this idea of local exploration then? So the use is the following. You have learned that there is a possibility of walking in a more intelligent way, and now we will keep adding more intelligence into it, okay, till the time we reach order n algorithm. So the next thing we can do here in local exploration is so what is the next thing? So that is best explained in a 1D array. Okay, let's move to a simpler case. Yeah, so in the case of a one-dimensional array, we will adapt binary search with this exploration to get a very, very fast algorithm, super fast. So let's make this idea more clever by looking at a 1D array. So the 1D array, let's call it now A, n elements. And again, the same question, you want to find here a local minima, right? So in this case, the picture will always be, or will generally be like this. So what did we use? 5, 3, 4 and J. So in the case of 1D array, there are either there is only one neighbor or two, or it can be 0 also if you have a single element. So the neighbors can be 0, 1, 2. Generally it is 2, and so again you can talk about local minima, a green cell which is locally smaller than the other two, the adjacent ones. So how fast can you find this in a 1D array? Yeah, so brute force is order n, and why do you say that you can use binary search? That's a bold claim. If you remember binary search, it never works for an unsorted array. Binary search requires a dictionary or a sorted array. So how come you became so bold in the 6th class that you can claim binary search here? What is the reason for binary search? It's a random array.
Because it checks the next integrous element. So it's smaller than
No, it checks halves. It takes, it basically decides from the midpoint whether to go left half or right half.
So, but we need only one answer if it's smaller than both of them. That can be possible through a binary.
Right, but the answer will not come by looking at just mid. So let's say green one is the mid. So where will the binary search kind of idea decide to move now? The right half or the left half? Sorry? Smaller than. So yeah, in this case, of course not, but suppose the left value is 1 and the right is 2, then what will happen? Yeah, then it should go on the side which is smaller than 3, which is 1, which is on the left. So it will go to the left half. I mean, this would be the idea. You have to analyze this. There is right now no reason why it should work. So the idea here is locally explore using binary search. And the middle values. So mid equal to left plus right by 2. Okay, so we will be applying binary search based on the midpoint, the entry at the midpoint of the array. The markers will be in general L and R, okay, which initially you start with 0 and n minus 1. So let us see why. Let us see first of all what are we doing here. So the pseudocode is so if A mid is not local minima, in the whole array, so that is left to right, then there is a chance to halve the array. Right? Either go to the left half or the right half. So we should take that chance and move to a neighboring smaller element which can be mid -1 or mid +1. So one of these is smaller. Say you go to the smallest and say the smallest is mid -1. So this is smallest of the three, right? So mid -1, mid and mid +1 amongst these, let's say mid -1 is the smallest. So you should be picking the left half. That will be the algorithm. So, and move to that half. Okay, so that is the pseudocode fragment. So in picture you can see it like this. So these are the endpoints of the array that you are at. While the binary search recurses or as it iterates, you will be in some part of the array, subarray, l+1 ... r, and the midpoint will be located here. And these are mid -1, mid +1. And suppose the smaller one is here. Is the smallest of the three. So then you should update your subarray, which means that should you update L or R? Yeah, so L, the left endpoint doesn't change, the right endpoint should change. So R should be updated to mid -1. So from here to here, so left half is used next, which means that the right endpoint is updated to mid -1, and L remains the same. Okay, so this is the implementation of binary search without assuming sorted array. Right, we are just locally seeing and moving to the smallest of the three part. So how do you show that this works?
If we consider like a function which takes indices and then loads the values that's stored in indices, and we move towards the negative of the gradient of that function, which ultimately leads to the local minimum. You can choose any point in the function and continue moving towards the negative of the gradient.
Yeah, that is what we are targeting. What is the proof?
So negative of that gradient will ultimately descend that function.
But what is the meaning of gradient here? These are discrete values. There is no curve. So what you are saying in the continuous word, we can actually simulate it here in the discrete word also. But we have to do this properly. So you cannot invoke that as a theorem, because this is not that situation. Yes.
Actually, in this, we will move toward mid minus 1. If mid minus 1 is not, then mid minus 2. So wouldn't it be n by 2?
No, no, no. See, we are not moving mid. We are changing L and R. So, well, that is then your first observation you have to make, that the L new minus R new, how does it compare with original L and R? Does it only reduce, or can you say more? It's actually half here. So the length of the array is halving every time. Okay, so this is what binary search does. It reduces the size of the array by half. That is not the problem here. The problem is, why is this correct? Why does it give a local minima? That is what we try to show. That is what is left to show. So, well, the proof of the above, if you are confused, is just by midpoint. Since we consider the mid each time. So since you are considering the mid, you only have two halves. So every time the length is halved. That's not the issue. So you have to write down an important invariant here to finish the proof. The important invariant is when you move to mid minus 1, what has happened is that element is smaller than its right boundary, right? And similarly, this the entry at L, the first endpoint, that is also smaller than its left neighbor. So we can ensure this invariant, I mean, if it exists. If L is the very first starting point, of course, you don't have anything on the left. So either you don't have anything on the left, or if you have something on the left, then that is bigger. Okay, so we will write down this invariant, and we will show that this invariant holds in every iteration. So the invariant being that the two endpoints, when you move from left to further left, value increases, and when you move from right to further right, the value increases. Okay, that's the invariant. So the process satisfies or ensures the following invariant, which is the cornerstone of our whole algorithm. So this invariant is, so let's make it a lemma. That L minus 1 value and L value and the R value and R plus 1 value. So there is a relationship in these two pairs. So as we have seen in the previous, in this picture, in this dry run of the pseudocode, that when R is updated, so R new value is smaller than R old value. So we can write that confidently here, and same thing here. Okay, these are the two inequalities which will always be preserved. That left to R endpoints, their values are smaller than their outer elements, the respective outer elements. So this proof is if this L minus 1 or R plus 1 are outside, I mean, or they don't exist, then it is vacuously true. And when they exist, the I mean, this pseudocode which we had, the pseudocode iterates following this inequality. So if you just think about these 2 points, you will have the proof. So L, when you started, then L was 0 and R was n minus 1, and there was nothing beyond. So before 0 there was no element, and after n minus 1 there was no element. So this inequality, we considered it to hold there vacuously. And then the first time you come to the midpoint and you change R or you change L, the pseudocode will preserve one of these inequalities. It will make sure that it holds. Okay, and once it holds in this step, it holds in every step. Is that clear? So formally you have to say that it follows by induction. Induction on the number of iterations. Okay, so you have to be clear about these phrases. What is the induction on? What is the base case? And what is the induction step? So in the base case is 0 n minus 1 case. Induction step is the pseudocode itself. This is what takes you from one step, from one L comma R or L old R old to L new R new. And then once you have these two things set up, induction proceeds as it always proceeds in math. Right? You have a proof. Is that clear? It's a very simple observation, but I am sure half of you will be confused about this. So you have, if you are in one of those halves, then you should think harder. Yeah, so this then completes our array, this 1D array case. So we have what we can deduce now is that it finds, or this algo finds local minima of 1D array in how many steps? Yeah, so the number of iterations is log n because every time you are halving. And in one induction step or in one iteration, you are doing just trivial checks, inequalities, constant time. So it's order log n. Let's say steps. I'm ignoring the numbers, how big the integers are. So integers are big, then the comparisons will also be big. But otherwise, I mean, other than that, it's log n steps. Yeah, so this proof has to be written. Just one last step. So how is the lemma implying this theorem? How did that inequality tell you that in the end you have a single answer?
cut the array into half, we are always ensuring that there always exists a local minimum.
No. Yes, I mean that is true, but I'm not saying that yet. I just want the lemma statement. Let's say we number it. So let me say this is lemma 1. And this one is lemma 2. So now from lemma 1 and lemma 2, I want to just directly deduce the theorem. So how do you do that? Yeah, so you use that property. You basically apply lemma 2 again and again, log n many times. And in the end, what will happen is L and R will become equal. Because L is increasing and R is decreasing. So at some point, they will try to cross each other. And at that point, you will halt. Right? So the crossing point is where L and R actually become equal, so you get one element. So interval becomes a singleton. That is the proof. So these are the things that you have to formally work out and write. If you don't write everything, we will consider it a bluffing proof and not a proper proof. So by lemma 1, there are log n steps. At the last step, what will happen is that L will become equal to R. Because the interval is always shrinking, so at some point it becomes singleton. Just before becoming empty, it has to be non-empty. And when it is non-empty, it is size 1. So at the last step, L is equal to R, which means this element AL and AR are the same. Is a single element. Single element, let's say X. So we have identified a single element X at the end, and what is the property of this single element? So by lemma 2, the property is that AL minus 1 is more than X, and X is less than R plus 1, which implies that X is a local minima. Okay, so this is what you have to write. This is the formal proof. You have two lemmas, each sounding very simple. But still, when you prove it, you will see you have to give a proper proof. And then those two lemmas give you, after several iterations or after several applications, something brilliant, that this single element is actually a local minima. Because it is at L, and if you look at L minus 1 or L plus 1, both are bigger. Right? So it's a super fast algorithm to find local minima in an array. So maybe I can write the pseudocode. So L will be initialized to 0, R will be initialized to n minus 1, and there will be a variable, for, let's say, found, initialized to false. And while not found, you calculate the midpoint if A mid is local minima, then you will say found is true. You will set it so that you go outside you break the while loop. Otherwise, you have to do the binary search thing. So which side to move? So if A mid -1 is less than A mid, then you should be moving to the left half, which means you should be updating the R. Else L. So you bring L forward, which means that you are looking at the right half. Okay, so that ends the while loop. And now you have found the single value. So return A mid. That's the local minima. Okay, so here I'm moving just one of the smaller neighbors. I'm not looking at the least, but you can also look at the least. It's the same thing. When you have two options, maybe it is wiser to move to the smaller one. But even this is fine, the same algorithm. Yeah, so for this pseudocode, you have that theorem. Okay, that this takes time, order log n. Any questions? But this is still a very small part of what we wanted to do in the class. Right, so bigger things we'll do tomorrow. So question you have to answer tomorrow is, can we extend this from 1D to 2D? Right, so can this 1D array idea be generalized to 2D?